Have you ever wondered what would happen if you accidentally tumbled into a black hole? I mean, we've all had that thought while taking out the trash on Tuesday night, right? No? Just me then. Imagine this. You're an astronaut on a routine space mission when suddenly your tether snaps. You begin drifting, slowly at first, then faster and faster toward that infamous cosmic vacuum cleaner. That point of no return. The universe's ultimate do not enter sign that, ironically, you can't even read because light itself can't escape. What would you experience in your final moments? Would you be crushed instantly, stretched into cosmic spaghetti, or perhaps transported to another universe entirely? Today we're going on a one-way journey to answer the question that keeps astrophysicists up at night and makes insurance companies add that special void where prohibited by laws of physics clause. What actually happens when you fall into a black hole? Buckle up, space travelers. This ride gets weird. So you're falling toward a black hole. First of all, congratulations on being part of the most extreme sport in the universe. Your GoPro footage would break the internet. If only the signal could escape. The first thing you'd notice is the immense gravitational pull. Unlike Earth's gravity, which pulls relatively uniformly across your body, a black hole's gravity has an incredibly steep gradient. This means the gravitational force on your feet would be significantly stronger than on your head. At first, this difference is subtle. You might feel a strange tugging sensation, like you're being pulled in multiple directions at once. Not uncomfortable yet, just odd. The stars behind the black hole would appear to wrap around it, forming what astronomers call an Einstein ring, basically the universe's version of a funhouse mirror. As you get closer, though, things start getting interesting. Time itself begins to warp. From the perspective of a distant observer, let's say your colleagues back on the spaceship, who are probably filling out a lot of paperwork right now, you appear to be moving slower and slower. Your radio messages to them become increasingly stretched out and redshifted. "Help me" might take minutes or even hours to be heard from their perspective. But from your point of view, time is passing normally. In fact, you might look back at your ship and notice that everything there seems to be speeding up. Your crewmates are zipping around like a comedy fast-forwarded while you're experiencing the universe's most terrifying slow-motion fall. This is Einstein's relativity at work, and it's the first sign that you've entered a realm where the usual rules of physics are beginning to bend, much like your inevitable future. Now we arrive at everyone's favorite part of black hole physics, a process with the delightfully culinary name, spaghettification. Though I must warn you, this isn't the kind of pasta experience anyone would enjoy. As you continue falling, that difference in gravitational pull between your head and feet becomes more pronounced. We're not talking about a gentle tug anymore. The gravitational force on the part of your body closest to the black hole becomes exponentially stronger than on the part farthest away. What does this mean for your astronaut body? Well, you begin to stretch. First, it might feel like the world's most aggressive yoga session, then like you're on a medieval rack. And finally, your body literally begins to elongate into a thin stream of, well, human spaghetti. If you're falling into a supermassive black hole, like the ones at the centers of galaxies, this process might actually be relatively gradual. You could potentially survive crossing the event horizon before becoming cosmic pasta. Think of it as a small mercy from the universe. But for smaller black holes, the spaghettification would begin well before reaching the event horizon. The technical term for what happens to you is tidal disruption, which sounds almost polite, like something a British person might say. I do apologize for the tidal disruption, good sir. But in reality, it's the universe's most extreme stretching exercise. Your atoms are pulled apart into a long, thin stream of particles that continue their journey toward the center. On the bright side, if anyone ever asks if you're flexible, you can truthfully answer that you once touched your toes while your head was several miles away. Assuming you've somehow maintained consciousness through the spaghettification process, which, let's be honest, is highly unlikely, but makes for a better story, you'll now cross the point of no return, the event horizon. This is the boundary where the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing that crosses this boundary can ever escape. It's nature's ultimate "what happens in Vegas stays in Vegas" line. Except Vegas is a singularity of infinite density, and you're about to become very, very acquainted with it. The fascinating thing about crossing the event horizon is that, from your perspective, nothing special happens at that exact moment. There's no flashing sign, no cosmic turnstile, no existential bouncer checking your ID. If the black hole is large enough and you've somehow avoided becoming spaghetti, you might not even notice when you cross it. It's only special because it's the point from which you can never, ever send a message home again. Once inside, something truly bizarre happens to the very nature of space and time. The roles of space and time effectively swap. Outside the black hole, you can move freely in space, but time always moves forward. Inside the event horizon, time is frozen in a sense, but space only moves in one direction, toward the center. Just as you can't decide to move backward in time under normal circumstances, inside a black hole, you cannot decide to move away from the center. Every possible future path leads to the same destination, the singularity at the center. It's like being stuck in a cosmic water slide with no way to climb back up, no matter how hard you paddle. And the singularity itself? That's where our current physics breaks down completely. A point of infinite density and zero volume, where all the mass of the black hole is concentrated. What happens there? Well, that brings us to our next section. So what ultimately happens to you and all the information that made you, you? This question has puzzled physicists for decades and leads to one of the greatest conundrums in modern science: the black hole information paradox. According to classical physics, you and all your information, the quantum states of all your particles, your memories, that embarrassing photo from your college years, would be irretrievably lost in the singularity. Gone, kaput, written out of the universal ledger. But this creates a massive problem. Quantum mechanics insists that information cannot be destroyed. It's one of the fundamental rules of the universe, like the fact that nothing can travel faster than light, or that pizza always tastes better at 2 a.m. So we have a paradox. Black holes seem to destroy information, but quantum physics says that's impossible. It's like when your mom said wait an hour after eating before swimming, but your dad said that's nonsense. Someone has to be wrong, but who? In the 1970s, Stephen Hawking proposed that black holes might slowly evaporate over time through a process now called Hawking radiation. Tiny particles pop into existence at the event horizon through quantum fluctuations, with one falling in and one escaping. Over unimaginably long periods, this causes the black hole to lose mass and eventually disappear. But this created another problem. If the black hole eventually evaporates, what happens to all the information it consumed? Does it somehow come back out with the radiation? Is it encoded on the surface of the event horizon like some cosmic hard drive? Or does it create a gateway to another universe entirely? Some theories suggest that instead of encountering a singularity, you might pass through a wormhole into another region of space-time, perhaps even another universe. Instead of being crushed into oblivion, you'd be the universe's most extreme immigrant, arriving in a completely different reality. Other physicists propose the firewall hypothesis, suggesting that the event horizon isn't the smooth boundary we think it is, but rather a wall of high-energy particles that would incinerate anything crossing it. This would solve the information paradox, but would mean a very toasty end to our hypothetical journey. The most recent ideas involve quantum entanglement and holographic principles, suggesting that information might be preserved in subtle quantum correlations at the event horizon. Essentially, a perfect record of you might exist as a kind of quantum shadow on the boundary of the black hole, while the physical you continues toward the center. So the real answer to what happens to you inside a black hole, we honestly don't know for sure. And that's what makes black holes so fascinating. So there you have it, a journey into one of the most mysterious objects in our universe. From time dilation to spaghettification, from event horizons to quantum paradoxes, black holes challenge our understanding of reality itself. The good news is that you're extremely unlikely to ever fall into a black hole. The nearest one to Earth is thousands of light years away, and they don't exactly roam the galaxy looking for snacks. Though if they did, I imagine Earth would be more of an appetizer than a main course. But our fascination with these cosmic monsters goes beyond mere curiosity. Black holes represent the frontier of our knowledge, the place where our most successful theories of physics break down and hint at deeper truths we have yet to discover. They force us to confront fundamental questions about the nature of space, time, information, and reality itself. They remind us that the universe is stranger than we can imagine, and that there are still profound mysteries waiting to be solved. As we continue to observe black holes through increasingly sophisticated methods, from gravitational wave detectors to the Event Horizon Telescope, we edge closer to answers. Each discovery brings new questions, each solution reveals new puzzles. And that's the true wonder of science. Not that it gives us all the answers, but that it leads us to better questions. Questions that take us on journeys through the cosmos and deep into the nature of reality itself. So the next time you gaze up at the night sky, remember that somewhere out there, these cosmic leviathans are spinning through space, bending light, warping time, and challenging our very understanding of existence. Just maybe keep a safe distance. After all, falling into a black hole might make for a great science video, but the return trip would be problematic.